Okay, so Chapter 18 is kind of a change of pace after 4 chapters of equilibria. This is introducing new material, but really this is revisiting some of what we did in Chem 111. In Chem 111, we start off with the heat and energy chapter, and we looked at only one facet of thermodynamics, the energy exchange in chemical reactions. We learned about enthalpies, and you remember Hess's law and enthalpies? And you remember that when something is exothermic, heat exits the system, it has a negative sign. When something is endothermic, heat is entering the system, or heat is a reactant, and it has a positive sign. So we talk about the energy of the system, and we look at the internal energy of the system, which was previously defined as total energy, and we use the letter E. So the energy of the system can be thought of as the kinetic energy plus the potential energy. Now, I'm going to go through these first few pages kind of fast, just running through them. Everything's written down, and I'll tell you the important stuff you need to know, but I want you to see where it all came from. So since we think of our energy E as a state function, remember a state function only depends on where it is now. It doesn't matter where I was before or what path I used to get there. So the change in energy is final minus initial. So for us in chemistry, it is the energy of the products minus the energy of the reactants. And we know that energy has both a heat and a work term. So we use Q for heat and W for work. And this is an important definition because this tells you which way the sign goes. Q is the heat absorbed by the system, and W is the work that is done on the system. So if Q is positive, heat is absorbed. If Q is negative, then heat's released. And there will be questions where you will have to recognize what the positive or negative sign means, and there will be times when you may have to change the sign to fit those definitions. When we talk about work, if W is positive, work is done on the system, and when W is negative, work is done by the system. Now, the change in energy, or the internal energy, is a state function. It doesn't depend on path. But heat and work are not state functions. And so we can define our work. For us in chemistry, it's usually in gases with pressure-volume work, changes in pressure or volume. And work is equal to minus P delta V. Another definition of work that you see mostly in physics is that it's force times length. And so we think of force times length, and that is moving a piston generally for us in chemistry. So pressure is a force defined as force per area, so our work is minus P delta V. If we have a system at constant volume, it means volume isn't changing, so delta V is 0. So if delta V is 0, delta E is Q plus W. Delta E is Q plus W, and W is negative P delta V. And if delta V is 0, delta E is Q minus 0. So delta E is Q. And this is what you need to know at constant volume. That if we have a system that it is at constant volume, then the change in energy only has a heat term. There is no work, so we just work with the heat in terms of chemistry. Now, occasionally we have something where it's in a sealed container and we're at constant volume, and that applies. It's more common for us in chemistry to have reactions done at constant pressure. And they're done at constant pressure in the laboratory. So we're always making that assumption that the pressure of the laboratory room is not changing. And most of the times that's not the case. I know that I have experienced some things when I was doing gas laws in Chem 111. We had a big storm system coming in, and so the atmospheric pressure dropped tremendously during the 3 hours that we were in lab, and it really messed up our results because we had measured the pressure earlier and then continued to work, and the pressure was dropping rapidly. So constant pressure is what we typically do in chemistry. And when we talk about the enthalpy, which is what was introduced for you in Chem 111, enthalpy is the heat that is evolved at constant pressure. And again, It's because the enthalpy is the energy plus the pressure times the volume. So the change in enthalpy, delta H, is the change in energy, delta E, plus delta PV. When P is constant, then P is, delta PV is 0. So delta H is delta E plus P delta V, and delta E is Q minus P delta V. So we get delta H is Q minus P delta V plus P delta V. So again, when we're at constant pressure, the enthalpy change is just heat. So delta H is defined as the heat of reaction at constant pressure, and delta E is the heat of reaction at constant volume. And they are related to each other in that the change in enthalpy minus the change in energy is equal to P delta V. So, how do we work to go from one to the other, to convert enthalpy to energy and vice versa? If we think of this system containing an ideal gas, we know the ideal gas law, PV equals nRT. So we can rearrange this that the volume is equal to nRT over P. So delta V is equal to delta nRT over P. And if we have a system where we are holding the temperature and the pressure constant because we're working under a well-defined state of our system, then the temperature is constant, the pressure is constant, R is always a constant, that's the gas constant. So delta V is equal to delta N times RT over P. So we can substitute back in. Delta H is delta E plus P delta V, so delta H is equal to delta E plus P times delta RT over P. Well, P times delta RT over P, the P cancels, so delta H is equal to delta E plus delta N sub G times RT. And this is the final relationship between enthalpy, H, and internal enthalpy, internal energy, delta E. So, this is an equation that you will have to know. Put this on your list that you keep at the front of your notes with a list of equations.